So in this video, we want to prove Hall's theorem that gives us a necessary and sufficient condition for a graph to have a bipartite graph to have a matching. So what does it mean, right? Like, what do we want? We have a set A here and a set B here. And what we want to find in this situation is we want to find a matching that covers all the vertices in A, and there could be leftover vertices in B, of course. So we want to find a number of independent edges, non-intersecting edges, that cover all the vertices of A. One thing, so I said necessary and sufficient condition. What is this condition? The condition is the following. If I look at any set in A, any subset of the vertices, including a single vertex or all the vertices, if I look at all the neighbors of these vertices, maybe this is the neighborhood of the subset X, n of X, has to be at least as large as the set X. This is a necessary condition. Why is this a necessary condition? Well, if we do find this red matching, then every vertex in X has a matching neighbor in the neighborhood of X. So the matching neighbors in the of X, of course, are as many as the vertices in X. So we could have additional neighbors in the neighborhood, but we must have at least that many. So this direction, that it's a necessary condition, is fairly obvious. But now the question is, how do we prove that this condition is also sufficient? So let's get started. So we will prove this using induction on the size of A, of that left set that gets matched, how we say. So the start is very easy. We could start with the size 0 or 1. Both are easy. So 0, this is true, and it's trivial. Why? Well, if A has the size 0, a matching contains no edges, and no edges cover all the vertices, all the 0 vertices of A, so everything is fine. So so the induction start works. So how do we go on? Well, what is the idea here, right? Like, the idea is the following. Here again, here's my set A, and here's my set B. One way of doing this, one idea could be, well, maybe we can find some edge xy so that if we take these two vertices out of our graph, the remaining graph still satisfies Hall's condition. So whenever I take a set X in A and look at the neighborhood of X over here, where of course I cannot use Y in this neighborhood now, and X better not contain, the big X better not contain the vertex X. So whenever I have a picture like this, this neighborhood needs to be at least X. If I have a situation like that, then I could apply Hall's theorem to the smaller set A minus X and the smaller set B minus Y, right? So here's my set A minus X. Here's my set B minus Y. If I can apply Hall's condition here and find a matching here, this matching together with the edge XY is the matching I'm looking for. So this is my goal. This is maybe what I want to do. Okay, good idea. What could go wrong? Well, one thing could go wrong is that there is a set X for which in this new graph the neighborhood is smaller than X. How could this happen? Well, let's see. It could look like this. So we could have a set X that does not contain little x. The neighborhood of X does contain the vertex Y, and the neighborhood of X is exactly the size of X. In this case, we are still Hall's condition in the original graph, but the smaller graph where we removed the vertex X and the vertex Y does not fulfill Hall's condition anymore. So if we have something like that, then there is a problem. So to write this down, so idea, let's write it over here. Idea delete X and Y, and we get a graph G prime, A minus X, B minus Y, something like that, right? On these sets, it's of course still a bipartite graph, and we have two cases. First, G prime fulfills Hall's condition. That's our first case, in which case, what do we get? Well, use induction to find a matching in G prime, and together with XY, this is a matching in G, and we're done, right? So the first case is easy. So let's consider a second case, and for this I'm going to clean the board. Okay, so here is our second case. The second case is that there exists the set large X in this left side of the G prime graph that is a witness of Hall's condition being wrong in the G prime graph. What does this mean? Since Hall's condition is true in the graph G, it means that the neighborhood of the set X is actually the same size as the set X in the original graph, but since the vertex Y is in this neighborhood, in the new graph G prime, Hall's condition is violated because in the new graph, the neighborhood of that set X is one smaller than the set X itself. What can we do with this? Well, first of all, let's look at this graph that's just spanned by X and the neighborhood of X. Like, let's just look at that. Whenever, like, first of all, of course, X is smaller than A, so we might be able to use induction. So we could check if Hall's condition is true in this graph. Well, any subset of X, call it Y, the whole neighborhood of that subset, of course, lies in the neighborhood of X. So therefore, if I just concentrate on the green graph, the sizes of the neighborhood in subsets of X are just the same as the size in the original graph, because they must live in there. So therefore, by Hall's condition, or therefore Hall's condition is true for this green graph here. So Hall's condition is true for this graph on restricted on just this pair. And therefore, by induction, we have a matching in this graph. So somehow we can find a matching over here, which matches all the vertices of X actually to vertices in N of X. In this case, there's no vertices left over on the right side because the sizes of X and N of X are the same. So what do we know about the rest of the graph? So the idea is now that forget about this edge between X and Y here that we know, right? The idea is now, in this case, we can match X to N of X. And now let's take any set over here and look at its neighborhood. What do we know? Well, part of its neighborhood. So if we look at this neighborhood of this graph, this set Y here, this neighborhood of Y over here, well, what do we know? Well, this picture, like you see it, is not helping too much because, well, we want to use the red matching that we have already and make it to a whole matching of the whole thing. So if the neighborhood of Y intersects the neighborhood of X, that's not helping because we cannot use the vertices on the neighborhood of X as neighbors of vertices in Y in that whole matching. But what do we really know? Well, let's see. What we have to look at instead of the set Y, what we want to look at is the set X union Y. So Y is now a subset of A minus X, right? And we look at the set X union Y. Then of course, this set by Hall's condition is at most the size of the neighborhood, or the other way around. The neighborhood has at least the size of the set. But this left side, of course, since Y and X are disjoint, is just X plus Y. And this right side, of course, we can write as the neighborhood of X plus the neighborhood of Y minus the neighborhood of X. And now we know that these two guys have the same size. Since these two guys have the same size, we get that this guy is less or equal to the size of that guy. So up here in this picture, this was our Y here, right? The size of this Y, I'm using wrong colors right now, but stay with me, of this Y is actually bounded above by the size of this N, the neighborhood of this Y. So this is great. Why is this great? Well, this tells us that in this graph, G, after we delete X and its neighborhood, this new graph, which is smaller, has Hall's condition. Okay, so Hall's condition is true for this smaller graph where I delete all the green stuff up there. So, well, then by induction, we have a matching. Where do we have a matching? We have it here in this one. And then we put the two matchings together. and we're done. So this is the proof of Hall's theorem. So again, to recoup, what did we do? Well, we had an idea. The idea was to just greedily grab an edge in my graph. Of course, the graph has to have edges by Hall's condition. So we greedily grab an edge x, y, and just remove both vertices x and y from our graph. If we're lucky, the remaining graph, which is smaller, still has Hall's condition. And then we can just use induction, find a matching on the remaining graph, and together with this edge that we grabbed, we find a matching of the whole graph. So this is if everything goes by plan, as we hope. We just grabbed any old edge, and if we're lucky and the condition holds for the remaining graph, we're done. Of course, we can't guarantee to be lucky, but what does it mean to not be lucky? It means that by deleting these two vertices, we break Hall's condition somehow. The only way we can break Hall's condition is if there is a set on the left that does not contain x, where the neighborhood did contain y before Hall's condition was true. So the neighborhood before of this x was at least as large as x, and afterwards Hall's condition is not true anymore, so the neighborhood afterwards has to be smaller. So what does this mean? It means before it had to be exactly the same size. And this is the trick that we use. If Hall's condition breaks after removing x and y, it means that we are in a special situation where we have a set x on the left side, which is smaller than the original a, where the neighborhood is exactly the same size. In the graph induced by this x with this neighborhood together, Hall's condition is inherited from the big graph, so we can find a matching in that graph. And if I delete x and the neighborhood of x, we can also show that Hall's condition is true for the remaining graph, and we can find a matching there. Putting these two matchings together, we have found our matching. So this was a pretty long video, but it's an important theorem and it's used all the time. I encourage you to watch it another time, maybe stopping, trying to follow the whole argument.